This is chapters 23 and 24, television and video display units and fiber optics and lasers. To begin with 23, television and video display units. The objectives for the chapter are to explain the steps in the transmission of a television signal, discuss the scanning process, identify circuits in both black and white and color television receivers and explain their functions, identify the size and makeup of a television channel, discuss a variety of television innovations including video cassette recorders, remote control, and satellite television, list the benefits of Hdtv, that's high definition television, and compare as compared to analog television, explain the difference between multicasting and data casting, discuss the compression technique of MPEG-2, and discuss the various flat panel technologies. Some of the keywords in the chapter are active matrix, advanced television systems committee, or ATSC, aspect ratio, brightness control, charged coupled device, or CCD, data casting, deflection joke or yoke, electroluminance, enhanced definition television, EDTV, feed horn, fine tuning, focal point, frame rate, geostationary orbit, high definition television, Hdtv, liquid crystal display or LCD, MPEG-2, multicasting, National Television Standards Committee or NTSC, passive matrix, and picture element. Other words or technical terms include pixel, polarized light, progressive scanning, raster, resolution, scanning, shadow mask tube, synchronization or sync, pulse, thin film transistor liquid crystal display, Tft Lcd, tuner, ultra high frequency or UHF, very high frequency or VHF, recorder detector, video detector, and video head. Television is a giant in the field of communications. Through television, entertainment, education, information, and advertising are all available to millions of people. And through satellite links, television can instantaneously bring the entire world into our home or office. This text will not address the detailed electronic circuits involved in the production, transmission, and reception of television signals. However, it is important for all persons interested in the science of electronics to have a basic knowledge of television and related information. Television signals. Taking a picture from a location and reproducing it in your home is a combination of several processes. First, a television camera must record the images to be transferred. Next, those images must be turned into radio waves and sent out into the air, or turned into electrical signals and transmitted through cables. Finally, the signals must be received and translated back into pictures. Television cameras. What looks like a solid picture is really an extremely large number of dots. In a black and white picture, these dots are varying degrees of black and white. They are called picture elements. Look closely at a photo in a daily newspaper and you will see that these picture elements are clearly visible. As a television camera views a studio scene, it sees the scene as a combination of these picture elements. The scene is focused on a photoresistive mosaic in the camera that consists of many photoelectric cells. Each cell responds to the scene by producing a voltage that is in balance with the strength of the light. These voltages are amplified and then used for modulation of the AM carrier wave. This wave is transmitted to the home receiver. A line drawing of a camera tube an image orthicon is shown in figure 23-1. The scene in front of the camera focuses on the photocathode through a standard camera lens system. The varying degrees of lights cause electrons to be emitted on the target side of the cathode. These form an electronic image of the scene. The target plate operates at a high positive potential. The electrons from the cathode are attracted to the target. The target is made of low resistance glass and has a transparency effect. The electron image appears on both sides of the target plate. At the right in figure 23-1 is an electron gun, which produces a stream of electrons. The speed of the stream is increased by the grids at the top and bottom of the figure. The grids are shown. The beam scans left and right and top to bottom and is controlled by the magnetic deflection coils around the tube. The moving electron beam strikes the target plate, and the electrons return to the electron multiplier section. The strength of the electron stream returning to the multiplier is balanced with the electron image. It provides the desired signal current for electronic picture reproduction. Scanning. Scanning is the point-to-point examination of a picture. In the camera, the electron beam scans the electron image. It responds to the point-to-point brilliance of the picture. The scanning system in the United States is the Interlaced system. It consists of 525 scanning lines. The beam starts at the top left corner of the picture. It scans the odd numbered lines of the scanning pattern, lines 1, 3, 5, 7, and so on, from left to right. At the completion of 262.5 lines, the electron beam is returned to the starting point by vertical deflection coils. The beam then scans the even numbered lines. One scan of 262.5 lines represents a field. One set of the odd and even numbered fields represent a frame. A representation of the interlaced scanning pattern is shown in figure 23-2. The frame frequency has been set by the Federal Communications Commission, or FCC, at 30 Hz. This means your TV receives 30 complete frames per second, or 60 picture fields of alternate odd and even lines per second. To the human eye, this appears as a constant, non-flickering picture. A device called a horizontal deflection oscillator causes the beam to move from left to right to produce 525 lines per frame at a frame frequency of 30 Hz. The horizontal deflection oscillator must work at a frequency of 15,750 Hz. That is 525 times 30. The vertical deflection oscillator causes the beam to move from top to bottom. The vertical deflection oscillator must have a frequency of 60 cycles per second. This is a field frequency. Closer study of the scanning process reveals that the beam scans as it moves from left to right. After it has read one line, it quickly retraces to the left and starts reading the next line in the same way we read a book. The retrace time is very rapid, but still shows a line in the picture. Therefore, the picture must be blank or must be black during this retrace time. Also, when the beam reaches the bottom of the picture, a beam must be returned to the top to scan again. The picture must also be black during vertical retrace, or trace lines would be visible. The oscillators that make the scanning and retrace voltage for both the horizontal and vertical sweep must produce a waveform as shown in figure 23-3. This is a sawtooth waveform. Notice the gradual increase in voltage during the sweep and the rapid decrease during the retrace. During the sweep, the rapid decrease, these voltages are applied to coils that surround the picture tube. These coils are called the deflection yoke. An increase in the strength of the magnetic fields in the coils causes the electron beam to move. See figure 23-4. Scanning at the studio and scanning on a television must be in step. For this to occur, a pulse generator triggers the horizontal and vertical oscillators at the studio. This same pulse is also sent over the air and received by the television set. This pulse, known as the synchronization pulse or sync pulse, triggers the oscillators in the receiver and keeps them at exactly the same frequency. Older televisions have horizontal hold and vertical hold controls. These controls are used to make slight adjustments so that the oscillators can lock in with the sync pulses. Newer televisions make the adjustments automatically. Composite video signals. All video signals are formed in the same way so that a television can be used in any geographic area. These standards are set by the FCC and are used by all TV broadcasting stations. The television signals received by TVs contain picture, video, and sound aural information. The video information is an AM signal. The audio information is an FM signal. The amplitude of the modulation is divided into two parts. First, the first 75% is used to transmit video information. The remaining 25% is for the sync pulses. See figure 23-5. Also, a system of negative transmission has been adopted. This means that the higher amplitudes of video information produce darker areas in the picture. At 75%, the picture is completely black. Look at figure 23-5 again. The percentage is shown on the left. As the beam scans each black bar, a similar action takes place. At the end of the line, the screen is driven back to the pedestal or blanking level. During this blanking pulse, beam flyback occurs and a sync pulse is sent in the blacker than black or infra-black region, the upper 25%, for oscillator synchronization. A second line to be scanned would be an exact copy of the first unless the picture is changed. At the bottom of the picture, a series of pulses trigger the vertical oscillator and keep it synchronized. Figure 23-6 shows a composite or complete video signal. The information for one line between the blanking pulses is varying degrees of black and white. Compare the two video signals in figure 23-7, bottom of the screen. Signal A is made up of mostly bright objects. The average overall brightness of the scene is another form of the information sent to a TV receiver from the transmitter. It can be detected from the composite video signal. Basic cathode ray tube controls. The cathode ray tube, or CRT, is used to produce images in television sets. The control grid determines the flow of electrons through the tube. In the CRT, this is also true, figure 23-8. A zero bias, or at zero bias, the CRT is at maximum current. Therefore, the screen is bright or white. At cutoff bias, the current is zero and the screen is black. The tube operates at a selected bias on the control grid. This bias can be controlled by the knob on the TV or a button on the TV remote called the brightness control. When no picture is being received on the TV, the scanning electron beam can be seen in the form of lines on the TV screen. This is called raster. Turn a TV on or turn a TV to a vacant channel and observe this raster. Now adjust the brightness control from black to bright. The incoming detected video signal is applied to the grid of the CRT, sometimes to the cathode depending on the polarity of the signal. The video signal adds to or subtracts from the bias on the tube. This action results in a modulated electron stream that conforms to the picture information in the video signal. The picture is produced on the fluorescent screen. The sharpness of or focus of the electron beam can be adjusted by changing the voltage of the focusing grids. From time to time, they may require adjustment. Refer again to figure 23-8. Find the centering magnet. Slight adjustments on this magnet will correct a picture that is off center. Moving on to review questions for 23.1. Briefly explain how an orthicon television camera works. The television camera views a scene as a combination of picture elements. The scene is focused on a photosensitive mosaic in the camera that consists of many photoelectric cells. Each cell responds to the scene by producing a voltage that is in balance with the strength of the light. These voltages are amplified and used for modulation of the AM carrier wave. This wave is then transmitted to the home receiver. Further, the scene in front of the camera focuses on the photocathode. Through a standard camera lens, the varying degrees of light cause electrons to be emitted on the target side of the cathode. These form an electronic image of the scene. The target plate operates at a high positive potential. The electrons from the cathode are attracted to the target. The target is made of low resistance glass and has a transparency effect. The electron image appears on both sides of the target plate. The electron gun, which produces a stream of electrons, is shown on the sketch. The speed of the stream is increased by the grids. The beam scans left to right and top to bottom and is controlled by the magnetic deflection coils around the tube. The moving electron beam strikes the target plate and the electrons return to the electron multiplier section. The strength of the electron stream returning to the multiplier is balanced with the electron image. It produces the desired signal current for electronic picture reproduction. And that is the basic explanation per the text how a television camera works. Question 2. Scanning is the point-to-point examination of a picture. 3. One scan of 262.5 lines represents a field. 4. What is the deflection yoke and what is its purpose? It is to manipulate the electron beam during scanning, and the deflection yoke is basically an apparatus that magnetically channels the stream of electrons from a television tube or CRT, cathode ray 23.2 Television Receivers. The television receiver is a fairly complex electronic device. As you work through the block diagram of the receiver shown in figure 23-9, take note of the similarities between the television set and the radio receivers you just studied in chapter 22. The black and white television receiver, figure 23-9, shows the parts of the this, see figure 23-10. The damper stage dampens out oscillations in the deflection yoke after retrace. The outputs of the sync amplifier is fed through a vertical integration network to the vertical oscillator. The integrator is an RC circuit designed with a time constant. The integrator builds up a voltage when a series or groups of closely spaced sync pulses occur. The transmitted vertical pulse is a wide pulse. It occurs at a frequency of 60 Hz. The vertical oscillator is triggered by this pulse and therefore keeps on frequency. The outputs of the vertical oscillator provides the sawtooth voltage to the deflection coils. The deflection coils move the beam from the top to the bottom of the screen and the flyback from bottom to top at the end of each field. The vertical outputs amplifier is used by the output of the oscillator to provide the proper currents in the deflection yoke for vertical scanning. Special purpose circuits. The basic television circuit has been improved in many ways. Automatic controls have been designed for many functions that would be tiresome for the TV viewer to manage. Two of these improvements are the DC restoration and automatic gain control. DC restoration. The average darkness or brightness of a TV picture is transmitted as the average value of the DC component of the video signal. If the video amplifiers are RC coupled, the DC value of the signal is lost. In this case, the average value of the video signal is taken from the detector and used to set the bias on the CRT. Automatic gain control. The AGC, or automatic gain control, serves the same function as it did in the radio receiver. Its purpose is to provide a fairly constant output from the detector by varying the gain of the amplifiers in the previous stages. This is done by rectifying the video signal to produce a negative voltage. This voltage is applied to the bias of the previous amplifiers to change their gain. Color television receiver. The color television was developed in the late 1940s. The system currently used in the United States was pioneered by RCA Laboratories. In March 1950, a color television demonstration was given in Washington, D.C. to FCC personnel, reporters, and other interested people. As a result of this demonstration, color television development was launched. An invention that made the color television possible was the shadow mask picture tube, picture 23-11. The three basic colors used in color television are red, blue, and green, figure 23-12. By combining these colors, any color can be produced on the screen. The first color picture tube produced for retail sale was the Delta type tube. It was invented in 1950 and was basically the same tube used in the color television demonstration given by RCA Laboratories in Washington, D.C. The Delta type tube uses 3 electron guns placed in the neck assembly of the picture tube. The electrons are emitted by 3 guns toward the screen. The screen is filled with hundreds of thousands of dots containing the colors red, blue, and green. In between the electron gun and the color producing screen, the 3 electron beams are focused through an aperture or shadow mask, figure 23-13. This shadow mask ensures that the electron beam strikes the dots properly. A line is made by one complete scan from left to right. All of 3 electron beams hitting the dots across the screen. If all the electron beams are adjusted properly, the result will be a white line. A color line is made by mixing the electron beams. Inline gun assemblies were invented after the shadow mask tube, figure 23-14. It shows 4 inline gun assemblies with different aperture, grill, and screen patterns. A color television receiver is a very complex instrument. It has to be able to produce both color and black and white pictures. But not all the televisions are color televisions, so the incoming signal must also work with black and white sets. Figure 23-15 shows a block diagram of a color television receiver. Television channel. The FCC has assigned a portion of the radio frequency spectrum to each television channel. There are 2 types of television channels: very high frequency, VHF, and ultra high frequency, UHF. Each channel is 6 MHz wide. The VHF channels, 2 to 13, are listed in figure 23-16, top of the screen, along with frequency bands and carrier frequencies. Examine channel 4 in figure 23-17 in the middle of the screen. The basic video carrier frequency is 67.25 MHz. Recall that when an RF carrier wave is amplitude modulated, sideband frequencies appear. These stand for the sum and difference between the carrier frequency and the modulating frequencies. To send a very clear, sharp picture, frequencies of at least 4 MHz are needed for modulation. These frequencies combine in channel 4 for a band occupancy of 63.25 MHz, that is 67.25 minus 4 MHz, to 71.25 MHz, that is 67.25 plus 4 MHz. It is a total channel width of 8 MHz. However, the FCC allows only 6 MHz, therefore a compromise must be made. In commercial TV broadcasting, the upper sideband is transmitted without attenuation. The lower sideband is partly removed by a vestigial sideband filter at the transmitter. The curve in figure 23-17 shows the basic response traits of the TV transmitter. The sound is transmitted as a frequency modulated signal at a center frequency 4.5 MHz above the video carrier. In channel 4, the sound is at 71.75 MHz. The ultra high frequency UHF television band covers from channel 14 to 83. As in VHF, the bandwidth of each channel is 6 MHz. The same frequency bandwidths are used for the picture carrier as VHF. The UHF channels used for commercial TV are set by the FCC. This is shown in figure 23-18. Review questions for section 23.2. 1. What is the purpose of an RF amplifier in a television receiver? The purpose is that it receives the TV signal in its entirety and amplifies it, then sends it to the mixer. 2. The output of the mixer stage is amplified by the answer is A, PIX IF amplifier. Question 3. Fill in the blank. The horizontal oscillator stage correctly shapes the sawtooth waveform for the horizontal deflection coils. 4. What is the purpose of a shadow mask? That is to ensure electron beams strike the basic colors or color dots properly. 5. A Sony Trinitron color tube uses a grill aperture. And question 6, each TV channel bandwidth is 6 MHz. 23.3 Television innovations. In addition to the electronics of television itself, there are a number of other electronic innovations that have made or that have been created to work with television. A few of these innovations are detailed here. The video cassette recorders. Video cassette recorders, or VCRs, can be used to play videotapes. They also can be used to record and play back television broadcasts. Most VCRs have 4 heads. A video head is a tiny electromagnet that reads information from the recorded tape during playback. It writes information onto the tape during recording. VCRs can have extra heads that provide better sound and picture quality. Look at figure 23.19. Recording information on a magnetic tape is simple. The tape is plastic with a thin coating of iron oxide on one side. The iron oxide is a magnetic material. The voice or picture message is converted to electrical impulses. These electrical impulses are applied to the coil winding on the recording head. The fluctuations of the electrical impulses make the magnetic recording head fluctuate at the same rate as the electrical impulses. The magnetic head induces a magnetic pattern on the metal oxide tape. The magnetic patterns uniquely match the original voice or picture patterns. The videotape not only records voice and video, but also speed information, end of tape location, copyright, and anti-copy coding. The digital video recorder. A digital video recorder, or DVR, combines computer and television components to form a television receiver. A DVR receives a television signal and can record the television programs as well. A hard disk drive is used for the recording medium rather than a magnetic tape as found in a VCR system. A hard disk is capable of recording and storing hundreds of hours of television programming. Remote control. A remote control is an application of infrared light and digital techniques. When a button on the remote's control is pushed, a digital code is sent out of the remote's control to an infrared sensor on the TV. The sensor on the TV amplifies and decodes the signal. Large screen projection TV. Most large screen projection TVs use a special Electron Gun assembly that projects 3 separate images onto a screen. Early projection TVs had screens with a significant curvature. As these televisions became more popular and more advanced, engineers were able to develop a flat screen projection. Figure 23-22 shows how the Electron Gun is assembled. The main performance problems with large screen or projection TVs is the loss of clarity in the video image. Remember, there are only 525 lines per frame of display. As the picture is increased in size, the lines become a distraction. The image does not magnify. It simply gets larger. Some large projection TVs offer a slight improvement in video image by scanning the same lines twice for a total of 1050 lines across each frame, or 1050 lines across each frame. These sets do have a sharper, more appealing video image to the human eye, but no real magnification has taken place. Satellite TV. Arthur C. Clarke first introduced the idea of launching satellites to improve communications. He did this in an article in the fall of 1945 issue of Wireless World magazine. He stated that if satellites could be launched high enough, that is 35,880 kilometers above the equator, they would be in geostationary orbit. Geostationary orbit means an object rotates with the Earth at the same speed The first communication satellite, Telstar 1, was launched by the National Aeronautics and Space Administration, NASA, in 1962. It was a small experimental satellite that only operated a few hours each day. This satellite made communication between the United States and Europe possible. In April 1965, NASA launched the first commercial satellite, Early Bird. This satellite was owned by the International Telecommunications Satellite Organization, Intelsat, a group created in 1964. Now there are many satellites in orbit, allowing for television, telephone, radio, data, and other communication messages. Rockets and space shuttles place satellites into space. There they are developed or deployed, and circuits are activated. Figure 23-23. This figure shows an SBS communications satellite now in orbit. This satellite was designed to provide voice, video, teleconferencing data, and electronic mail services to U.S. businesses. From its geostationary or synchronous orbit, 22,300 miles above the equator, ALSAT, Australia's first national communication satellite, links the entire country and Papua New Guinea through an advanced telecommunications system. When the satellite is in orbit, the antennas point south, making the spacecraft look upside down if viewed from Earth. Refer to figure 23-25 for that. Also, figure 23-26 shows the inside of a satellite. A traveling wave tube amplifier increases the strength of the communication signal for its broadcast back to Earth. It is being adjusted by an engineer. The amplifier is also on board a communication satellite. This satellite is built to carry both standard traveling wave tubes and solid-state power amplifiers. This type of satellite is reliable and has a long life. The diagram of the parts of a satellite are shown in figure 23-27. Figure 23-28 shows satellites in orbit over North America. Satellite transmission. Once a signal is made by a communication station on Earth, it is beamed up to the satellite. The satellite picks up the signal on its receiving antenna, amplifies the signal, and then sends it back down to Earth. The signal sent up from the studio to the satellite is a narrow targeted signal. The signal sent back down from the satellite is a wide signal designed to cover a large area of the Earth. The signal transmitted by the satellite is picked up on Earth by a receiving dish or parabolic antenna. The dish focuses the received signals into a small area called the focal point. The feed horn, which acts as a receiver, is located here. Located near the feed horn is a low noise amplifier, LNA, that amplifies the receiver or the received signal. The signal is then fed through a piece of electrical coaxial cable to the TV receiver. A coaxial cable has a conductor inside another conductor. The two conductors are insulated from each other. Figure 23-31 shows 4 dish designs. Rather, 2 dish designs. Motors are often used to move dishes. This way, signal from more than one communication satellite can be received, or the dish can be lined up with a particular satellite. A satellite receiver is shown in figure 23-32. This receiver can be programmed with infrared remote control. Complex circuitry allows the user to store satellite positions, polarity and frequencies, and tuning voltages into the memory. The programmed information can then be recalled from the unit's front panel or the remote control unit. Other remote control functions include volume control with mute, direct or scan channel selection, and video fine tuning. Coaxial cable. The signal that is supplied by the local cable television company or through satellite dish system typically connects to the initial receiver in the home from a single coaxial cable. Coaxial cable is designed to carry high frequency signals. The coaxial cable is designed to limit the radio waves generated from the center core conductor to the area between the core conductor and the shield. The shield will absorb the radio signal emanating from the core conductor when the high frequency passes through. Review questions for section 23.3. 1. Fill in the blank. A magnetic pattern is left on a recording tape. 2. A remote control sends a infrared signal to the TV. 3. How is an image projected into a large screen TV? That is with a special Electron Gun assembly that projects 3 separate images onto the screen. 4. What is the resolution limited for a typical large screen TV? And that is 525 lines per scan. 5. Who first proposed the concept of communication satellites? That is Arthur C. Clarke. 6. How does a receiving dish work? The receiving dish is usually a parabolic antenna. The dish focuses the received signals from the orbiting satellite into a small area called the focal points. The feed horn then acts as a receiver on the dish on Earth, and located near the feed horn is a low noise amplifier, or LNA, that amplifies the received signal. Then the signal is fed through a piece of electrical coaxial cable to the TV receiver. And question 7, which part of the coaxial cable is normally grounded? And that is the shield, or the outer surrounding conductor of the cable. .4 High Definition Television, or Hdtv. The analog television display system had remained the same for over 50 years without any major improvements to the quality of the transmitted image. This condition may have continued if not for the development of the computer monitor. The computer monitor had a greater image resolution than the analog television. By merging the analog television system with the digital system, many features that were not possible with the traditional analog system could be added. When converting the digital system, there was greater ability to manipulate screen images. For example, since there is greater color depth control in a digital system, images could be easily reapportioned as the image horizontal to vertical ratio changed between digital and analog television receptions. The FCC approval in 1996 of a digital television standard was the first step toward an improved and a higher quality picture. Although the switch to digital has progressed slowly, with more and more television stations switching to digital broadcasts and many digital television formats, high definition television (HDTV) has become the dominant digital television technology. HDTV allows for higher resolutions and a wider display screen than an analog display system. HDTV uses digital broadcasting techniques, allowing more information-rich data to be transmitted by airwaves than by analog broadcasts. Digital broadcasting can broadcast multiple channel in the same bandwidth as that used for the analog channel. Broadcasting multiple channels is referred to as multi. That is a digital camera to record images at the higher resolution, a digital receiver, HDTV tuner to convert received broadcast into image and sound, and a display unit capable of producing images at the high definition TV resolution. If any of these three major parts are missing, the HDTV system is incomplete and will not produce an HDTV picture. There are many television variations that use HDTV terminology but do not reproduce the desired HDTV effect. For example, a television system may be capable of receiving a transmitted HDTV broadcast but incapable of displaying the higher resolution HDTV image. Digital camera technology. Traditional analog televisions use vacuum tube imaging to capture images, while HDTV uses the charged coupled device, or CCD. The charged coupled device, CCD, is an integrated circuit consisting of an array of photo sensors that convert light from a camera's focused image to electrical energy. See figure 23-35. The level of electrical energy is directly proportional to the level of light captured by the photosensors. The CCD converts the individual packets of electrical charge into a series of analog signals representing the level of light amplitude at the photosensor location, and an analog to digital converter, ADC, converts the series of analog signals to digital signals. The digital pattern can be sent to a block computer memory to be stored in a still image, recorded to CD or DVD, transmitted across a computer network, or broadcast using the existing assigned television bands. For full color images, the high resolutions, 3 sets of CCD sensors are used. A beam splitter inside the camera separates the incoming light into 3 colors, blue, red, and green. Figure 23-36. Each color is sent to a corresponding CCD. The 3 images are then overlaid, producing a picture rich in color. Since the full array of each CCD is used for each color, the 3 CCD camera is capable of higher Hdtv resolutions. Hdtv picture quality. The most impressive attribute of Hdtv is the picture's visual quality. To compare the Hdtv image to the analog image, we must first convert the typical analog image to an equal digital resolution. The National Television Standards Committee, or NTSC, formulated the standards for analog television and video in the United States. The NTSC standards call for 525 scan lines at 60 Hz refresh rate on the interlace technique. The NTSC is not compatible with most computer video systems and must be converted before it can be displayed. The Advanced Television Systems Committee, or ATSC, was established in 1983. The committee spent years developing standards that were eventually adopted by the FCC for digital television broadcasting and receivers. These standards have been designed to eventually replace the NTSC standards. There are 18 scanning formats described in the ATSC standards. Variations in the standards are derived from concerns about interlaced scanning and progressive scanning, frame rates, and aspect ratio. Earlier in the section about the analog television system, you learned about interlacing. Interlaced scanning is a two-step process of transmitting the odd lines of the scan and then going back over the image, filling in the even lines to make a complete image. Figure 23-37. Progressive scanning is the capture and transmission of the entire image at one time. Each line is placed on the screen progressively in one sweep. Frame rate is how often the image is updated on the screen. Currently, 3 frames or 3 frame rates in frames per second exist: 60, 30, and 24. Aspect ratio is the relationship of the horizontal to vertical screen presentation measurements. Aspect ratio standards can be either 4:3 or 16:9. The 16:9 is a wide screen aspect ratio similar to common movie theaters. The 4:3 aspect ratio is a standard television rectangle. The various factors of aspect ratio, frame rates, and scanning method combine to form the 18 different screen standards. Figure 23-38 lists the 18 ATSC digital TV compression formats. Hdtv has a vertical scanning rate equal to 720p or progressive and 1080i interlaced vertical lines. The actual display may have a higher vertical rate than the 1080i standard. This is especially important as the size of the display area increases. To compare the quality of analog television to Hdtv, you must convert the scan lines to maximum number of pixels. A pixel is the smallest unit of an image on a graphic display. It can be thought of as a single dot in the entire image. Analog television approximates a screen composed of 480 by 440 pixels, producing 211,200 total pixels. Hdtv approximates a screen composed of 1920 or 1920 times 1080 pixels, producing 2,073,600 total pixels, and by far a greater detailed image than the analog system. The Moving Picture Experts Group developed the MPEG-2 image compression standard to increase the amount of video data transmitted in an Hdtv system. By compressing the broadcast video data, more information could be broadcast in the same amount of bandwidth. The MPEG-2 compression technique can reduce the image information as much as 97%, but an average of 50% is typical. The compression technique is based on the fact that the majority of the video images on a television screen do not change from frame to frame. For example, a news broadcast has a persistent image, such as a background, and with very little movement requiring new data. Parts of the image are persistent and do not need to be broadcast in each frame. This reduces the total amount of image information that has to be transmitted. The same technique is used for DVD, CDR, RW, and still cameras. Because more information can be transmitted using a completely digital system, sound quality has also greatly improved. Hdtv incorporates the 5.1 channel surround sound system into its standard. The 5.1 system is composed of a left, right, center left, surround, right surround, and subwoofer signal. This is the same quality audio used in the best stereo systems available. There are some misleading terms when used when describing advanced television systems. The fast evolution of these systems and terminology used by advertisers can often lead to disappointed customers. Enhanced definition television (Hdtv) is a system that receives digital transmissions and displays images at 480p or higher. The fact that it can receive high definition transmissions and decode them makes it an enhanced system. However, actual Hdtv display images at 720p or 1080i. You may have an Hdtv receiver connected to a display unit that cannot produce the higher display quality, thus defeating the purpose of Hdtv. Some systems simply take the existing NTSC system and double the number of scanning lines, but this does not provide any new image information. This is like using a photocopier to double the size of an original image. Since no new image information has been added, picture quality cannot be enhanced. Digital light projection television. One of the latest developments in television is digital light projection, DLP, developed by Texas Instruments based on the digital mirror device, DMD. The DMD is a precision light switch consisting of a rectangular array of microscopic mirrors. Looking at figure 23-39, each mirror is controlled separately. The entire array of mirrors span across one chip. A DMD can contain an array of over 1.3 million mirrors. The DMD technology is combined with a light source and lens to create a DLP system, which each individual mirror corresponds to a digital signal that represents a single pixel in the image to be created on the television screen. The array of mirrors can be switched on and off over 1,000 times per second. The length of time each mirror is switched on and off is used to produce an array of light and dark spots on the target screen. Varying the amount of time each mirror changes from light to dark will produce a specific shade of gray on the screen. For a full color image to be produced, the DLP uses a color filter. The reflected light passes through the color wheel at the exact moment that the required specific color is needed to produce the desired image into a screen. The transparent lens on the filter can create over 16 million different colors. A DLP television. A DLP television typically consists of a single DMD chip, a lamp, color wheel, and a projection lens. See figure 23-40. You can see the light source shining through the spinning color wheel. The light passes through the color wheel filter and then strikes the DMD as is reflected through the lens, which projects the image on the television screen. Flat panel displays. Flat panel displays have been associated with portable computer systems for some years now. As electronic display technology evolves, display units for computer televisions and other forms. The gas plasma display. The gas plasma display operates on the principle of electroluminescence. Electroluminescence is the display of light created when a high frequency passes through a gas to a layer of phosphor, resulting in the release of photons. The electrical energy from releasing photons is better known as producing light. A gas plasma display consists of millions of tiny cells sandwiched between two glass plates. See the figure at 23-43. Each cell contains an inert gas and is contacted or is coated with a phosphorus material of red, blue, or green. Transparent electrodes run horizontally behind the front panel on top of the cells, and address electrodes run vertically along the rear glass panel beneath the cells. When the address electrode and its corresponding transparent electrode are energized, the gas in an excited plasma state releases an ultraviolet light. The ultraviolet light strikes the phosphorus coating inside of the cell, causing the cell to release a light corresponding to its color. By varying the pulses of current, the entire light spectrum can be duplicated. Liquid crystal display panels, or LCD panels. The most common flat panel display is the liquid crystal display, or LCD. The liquid crystal display, LCD, operates on the principle of polarized light passing through tiny crystals of liquid. Light is composed of many different light waves. Each light wave travels at different angles. A voltage applied to the crystal causes the crystal to warp and in turn determine the amount of polarized light passing through the display screen. The LCD is classified according to the electronic circuitry and method used to apply light to the display's surface. There are two categories of LCD, active and passive. Passive displays are often more affordable and active displays because they require fewer transitions and are less complex. Active matrix displays are costly because they use one or more transistors at every pixel. Both active and passive displays are made up of groups of individual screen areas referred to as pixel areas. Each pixel area is made up of 3 color dots, or pixels, red, green, and blue. The combined effect of the 3 pixels produces pixel areas representing different colors. Varying intensity of each pixel can produce millions of colors. Combined with the surrounding areas, the pixels form an image on the display screen. How color liquid crystals displays work. To understand how LCD technology works, follow along with figure shown on the screen 23-44. The typical LCD panel is simple in construction. A backlight is required to generate the lights. The lights passing through the first filter result in polarized light. Polarized light consists of light waves, all the same shape of a single frequency rather than the entire spectrum of light frequencies generated by the backlight. The light passing through the first filter consists only of vertical waves. A liquid crystal sits between the two filters. When a voltage is applied to the liquid crystal, the molecules in the crystal rotate from the vertical position. When the vertical light passes through the energized liquid crystal, it too rotates, changing into a horizontal light wave that is blocked by the second filter. The second filter allows only vertical waves to pass through. The amount of voltage applied to the crystal determines the amount of rotation from the vertical position to a horizontal position. The more voltage applied, the less light that will pass through the second filter. The passive matrix display. There are two types of electrical circuitry used to energize the crystal area: active and passive. Figure 23-45. In a passive matrix display, a grid of semi-transparent conductors run to each crystal used as part of the individual pixel area. The grid is divided into two major circuits, columns and rows. Transistors running along the top and side of the display unit head the columns and rows. A ground is applied to a row and a charge applied to a column, which activates a pixel area. The voltage is applied briefly and must rely on screen persistence and a fast refresh rate. Because current must travel along the row and column until it arrives at the designed pixel, response time is slow. The active matrix display. In an active matrix display, each individual pixel in the grid has its own individual transistor. The active matrix provides a better image than the passive matrix. The active matrix image is brighter because each cell can have a constant supply voltage. The most common active matrix display is the thin film transistor liquid crystal display, the Tft Lcd. Often, this type of display is referred to simply as Tft display. The Tft display consists of a matrix of thin film transistors spread across the entire screen. Each transistor controls a single pixel on the display. There are over 1 million transistors in a display, 3 transistors at each pixel area, and 1 transistor for each color pixel. Figure 23-46 shows this arrangement. The liquid crystals in the Tft display are energized in a pattern representing the data to be displayed. The conventional television has used the CRT for display images because the original LCD design had limitations that could not compete with larger display units. As the size of the display unit grew to over 18 inches, problems developed with the brightness of the display and in converting the analog television signal to a digital signal and to a wide-angle viewing area without image distortions. These problems were solved with the introduction of thin film transistor LCD technology. The advantages of LCD displays over CRT displays. LCDs can be constructed much smaller and are lighter in weight than CRT displays. LCDs are more economical to run because they require less power. LCDs
generate less heat. LCDs create images that are more detailed. LCDs produce less electromagnetic interference, or EMI. Disadvantages of LCD displays are, as compared to CRT displays, is the lack of industry-wide standard, a higher cost for a comparable size, and complexity of scaling images without distortion. And this, of course, has all changed since the time of this writing. It's now 2018, and LCDs and even other technologies such as LED technologies have emerged and developed to the point where CRTs are no longer even available in the markets, and if they are much more costly. Display resolution. Resolution is a measurement of an image's quality. The higher the resolution, the higher the quality or more detailed the image. 23-47. Is one such unit designed to accept the inputs from many different sources. It allows a display to be used with television systems and PC systems as well. The Philips SXGA triple input display controller. To illustrate how one display system can be used in multiple applications, let's look at the Philips SXGA triple input TFT display system controller, figure 23-48. The triple inputs display system controller accepts input from analog, digital, and parallel sources. The analog input accepts the traditional UHF and VHF frequencies. The digital input accepts the Hdtv broadcast over cable, as well as from personal computer systems. The parallel interface accepts input from the sources such as USB connection devices, like a camera or a recorder. The block diagram of the SXGA triple input is different from traditional television. This system requires a microprocessor and special modules to process digital information. At the opposite end, there is just one input, the panel port. You will notice horizontal and vertical sweep controls, typical in a CRT imaging system, are absent in this unit. Since the image is digital, there is no need for such circuitry. There are several items in the display controller that are more commonly associated with a computer system. Standards organizations. There are several organizations presently creating standards for LCD type panel displays. There are as follows: the Video Electronic Standards Organization, the VESA, Digital Flat Panel, DFP, and Digital Visual Interface, DVI. The variance has caused much confusion concerning video display standards, not only for screen display resolution but also for standard connector construction. Look at the table, figure 23-49. For a brief summary of the three major standard groups involved in the development of a standard for their individual interest. The VESA work group is headed by the VESA Standards Organization. The DFP is led by Compaq, and the DVI is led by Intel. Each group consists of members from across the television and computer industry. Home theater connection types. There are many different connector types developed for Hdtv and various other displays. The display connectors are designed either for digital or analog transmissions, or for a combination of both digital and analog. Some manufacturers have tried to cut production costs by designing connectors to work with both television and computer systems. While making multiple application connections is reasonable, it has caused some physical and electrical incompatibility with design due to a lack of general standard for all manufacturers. As long as different standards exist, compatibility issues will arise between the devices from different manufacturers. Look at the various connector designs in figure 23-50. A home theater center can consist of many different electronic devices connected together. The equipment that comprises a complete home theater may involve a wide variety of cable connections. Audio cable does not require shielding from interface or cause interference the way video signals do. The speaker wiring has a low frequency that does not use a carrier wave because it transmits the sound pattern as an analog signal. Video cables must be shielded to protect the video signal from interference, and in turn, so the video cable does not broadcast radio wave interference to surrounding devices. You need to be able to identify each type of connection and understand its capabilities. The RF and F-type connections support the poorest quality video images and are found on the oldest technologies. The RF and F-type cables use standard coaxial cable made of a solid or stranded copper core conductor. The core conductor is surrounded by a thick insulator material. The insulator material is completely wrapped around by a conductive mesh of foil referred to as the shield. The shield protects the core conductor from outside electromagnetic interference. RF and F-type cables provide the poorest signal quality transfer between support home entertainment devices. For that, here 23-33. Composite video cables use only one cable for the video signal and two or more cables for stereo sound. Figure 23-51. The composite cable or video. The composite video will provide a better signal than the RF or F-type cable connections, but worse than the S or component video. The S video is a 4-pin connector that delivers separate signals for video signals, chrominance, color, and luminance, brightness. It is a very simple way to connect components together because there is no way to misconnect the audio and video cables. There is a 9-pin version that is used for video in and video out Vivo configurations. The 9-pin connector allows for video to be streamed in both directions. The 4-pin connector is used for applications that only require video in one direction. See figure 23-51B. Component video. The component video is found on high performance devices and produce better quality pictures than S-video or composite video. The cables used are constructed from flexible coaxial cable. Each individual cable consists of a single conductor surrounded by a dielectric and shield to protect it from receiving or generating interference. Figure 2351C. Component video does not carry the audio signal. Audio signals are typically supplied through 2 separate ports. High definition multimedia interface. The high definition multimedia interface, or HDMI, is used to supply video and audio in an uncompressed all-digital signal format. The figure 23-52 shows the cables used for this. HDMI supports high-definition television and Dolby 5.1 using a single cable. The digital audio is a high 192 kilohertz, and the digital video is as high as 350 megahertz and 10.2 gigabits per second of signal data. At the time of this writing, HDMI provides the best picture and sound quality available. The HDMI uses the new XVYCC standard, which is an enhanced color standard that exceeds the Hdtv standard. The HVYCC is short for Extended YCC Colorimetry for video applications. The term colorimetry means identification of colors using 3 sets of numbers representing red, green, and blue. This new standard was designed to enhance the viewing experience and can support 1.8 times as many colors as existing Hdtv signals. The new standard is also designed to support Blu-ray technologies for digital movie disc and newest video technology.
The Toslink optical connector, figure 23-52 part B, is a proprietary connection developed jointly by Sony and Philips. The Toslink cable is limited to audio at this time and is used to support audio Review questions for section 23.4. Question 1. What three things are needed to have a complete high definition television system? That would be a digital camera, a digital receiver, or an Hdtv tuner, and a display unit capable of producing images at high definition TV resolution. Question 2. What is multicasting? It is broadcast of different signals in the same channel, such as video, audio, etc. What is data casting? It is the broadcast of digital data, text, etc. Number 4. What does the acronym ATSC represent? Advanced Television Systems Committee. 5. What does the acronym NTSC represent? That is the National TV Standard Committee. 6. What does the lowercase letter I represent? And the summary for this all-encompassing chapter: a television picture is produced by scanning an image captured from a television camera onto a cathode ray tube. Scanning is the point-to-point examination of a picture. The scanning system used in the United States is the interlaced system. 9. Traditional analog television uses a vacuum tube imaging to capture images, while Hdtv uses CCD cameras to capture images and convert them to digital information. A digital camera uses a charged coupled device, or CCD, to capture an image and convert it to digital signals, and that can be stored or transmitted. A pixel is a single color element of a color pixel area. Hdtv is associated with display formats 720p and 1080i. MPEG-2 is the most commonly used video compression standard for Hdtv at the time of the writing. Dolby surround sound consists of 5.1 channels. The most popular LCD technology for high quality color images is the Tft Lcd. Test your knowledge questions for the chapter. Number 1, the dots that make up a picture are called dot matrix. 2, briefly explain the interlaced scanning system. And that is that it scans odd lines, then even lines, from top left to bottom right 30 times per second. 3, what causes an electron beam to move from left to right? That is the magnetic field in the deflector yoke of the television set. 4, the speed of an electron stream from an electron gun is increased by the answer would be A in this case, grids. 5, a composite video signal contains that would be both the video information and sound information, A and B, or the answer would be C, both of the above. 6, the cathode ray tube, that's fill in the blank question, in the CRT is used to produce images in most television sets that used to be popular at the time of the writing. Now, of course, that has changed. CRTs are no longer the most popular type of television set. 7, what are the 3 colors used to produce a color TV image? That is red, blue, and green. 8, what is the purpose of having more than 2 heads on a VCR? And other technology that's fast disappearing. And the answer for the question is for speed of recording and to record be a variety of signals, including sound, speed, and the copyright information. 9. Multicasting allows for 2 channels or 4 channels to be broadcast in the same single channel bandwidth. 10. To be considered a complete Hdtv system, 3 main components are required: a digital camera, a digital receiver, and a digital Hdtv capable of reproducing images at a high definition for a TV resolution. Question 11. The Video Electronics Standards Organization developed standards for digital television broadcasting and receivers. 12. 16:9 is a widescreen aspect ratio similar to that found in common movie theaters. 13. The Moving Picture Experts Group developed the MPEG-2 image compression standard to increase the amount of video data transmitted in an Hdtv system. 14. 50% of a typical transmitted picture does not change from picture to frame to picture frame. And lastly, 15. The most common active matrix display is the Tft Lcd, which of course has changed since the writing of this text. Moving on to the next chapter, fiber optics and lasers. The objectives for the chapter are to state the advantages and disadvantages of fiber optic systems, explain light theory, explain causes of light energy losses in fiber optic systems, explain the transmission of light as data, explain how light is received and gained and changed into data, explain how lasers operate, and list safety precautions to be taken when working with lasers. Fiber optics. Fiber optics is a relatively recent development in the electronics world and has met widespread acceptance. Fiber optics, as it is used in the electronics field, is the controlled transmission of light as a signal. Look at figure 24-1. The AM signal is converted to light and transmitted through the fiber optic cable. At the cable destination, the fluctuation light signal is converted back to an AM signal. You have already learned that copper wires as a conductor will accomplish the same goal. Let's look at some of the reasons why optic fibers might be a better medium. Why fiber optics? It may seem like extra work to convert an electronic signal to light and then to convert it back again to an electronic signal. One could question why the use of copper wire, where these conversions are unnecessary, would not be more efficient. There are quite a number of reasons a fiber optic transmission medium might be chosen over another conductor. The first is the fiber optic is lightweight and very small in diameter. Second, the fiber optic cable is corrosion and water resistant. Third, the fiber optic cable provides data security. Fourth, the fiber optic cable is immune to electromagnetic interference. Fifth, the fiber optic cable provides great deal of safety from fire and explosion. And sixth, finally, the fiber optic transmission has a wide bandwidth. These advantages are all important in different applications, so we will discuss each other further. We'll discuss each one further. Let's begin with weight and size. Fiber optic cables are exceptionally lightweight when compared to traditional copper wiring systems. This is important in general wiring applications, but a much greater advantage is gained when it is used in applications where weight is critical. Some of these uses are in aircraft and ships. The lighter the weight of the plane or ship, the more cargo it can carry. Fiber optic cables are approximately 1/10 of the weight of a comparable copper wiring system. Fiber optic cable has a smaller overall diameter than conventional cable systems. This is extremely important when running communication lines. Many more communication lines can be provided in the same conduit using fiber optics or fiber optic cable. In telephone lines, over 1,000 fiber optic lines can easily fit in the space where a system of 100 conventional cables once resided. Corrosion and water resistance. The very nature of glass or plastic makes it resistant to most corrosives. Water does not affect the light's conduction capabilities of a properly installed cable system. Fiber optic cables can be run under all of the world's oceans and are expected to last for many years. Security. In today's society, information is profitable and, in some cases, a priceless commodity. So it is important in business, industry, and military applications, and it must be protected against unethical people who would seek to gain from stealing it. It is virtually impossible to tap into a fiber optic cable without being detected on a secure communications line. Any cut made into the cable or cladding will disturb the light signal. Cutting into the cable completely disrupts the transmission of the signal. Removal of any cladding results in a loss of signal strength. At the present, fiber optic lines are secure. However, many systems throughout history have been viewed as virtually impenetrable, only to be compromised later. It should be emphasized that applied creative human intelligence can develop methods to compromise even the best security system. But for now, the fiber optic cable is far more secure than copper cable. Immunity to electromagnetic energy. Most of us have the annoying experience of having our television or radio signals interfered with by lightning strikes or the operation of an electric motor nearby. Fiber optic cable conducts light instead of electricity. This makes it immune to the electromagnetic interference generated by motors, radio signals, lightning, and other sources of electromagnetic energy. Conventional copper cable must be shielded to prevent electromagnetic interference. Adding shielding to a cable results in a cable that is much more expensive to produce, much larger in overall diameter, and a lot heavier. The military has a large investment in fiber optics and began the research in the field many years ago. The detonation of nuclear weapons creates a powerful magnetic field. This magnetic field is strong enough to destroy communication systems based on copper wire. The destruction caused by this magnetic field can occur many miles from an actual nuclear explosion area. Since fiber optic cable can withstand the electromagnetic field generated by even a nuclear weapon, military communications could remain intact for its use, or through its use. Safety. Fiber optics can be installed near explosive vapors, dust, such as in petroleum factories or food processing plants. This use eliminates the fear of an electrical spark caused by a shorted or grounded circuit using conventional conductors. In addition, light for illumination can be directly transmitted through fiber optics in place of conventional lamps. When using these electrical lamps for illumination in hazardous industries, the lamp fixtures must be a very expensive fixture, explosive resistant type. Fiber optic lamps are safer and cheaper. Bandwidth. The bandwidth available on a fiber optic cable has a superior merit when compared to copper. Light is transmitted at a much higher frequency than typical electrical signals. More signals can be transmitted at one time with fiber optics than with wire cable systems. Conventional cable systems have limitations and losses due to inductive reactance. Copper cables lose their conduction capabilities at extremely high frequencies. Fiber optic cable can handle high frequencies with little or no problem. The nature of light. There are two main theories of light. One theory addresses light as a wave, and the other treats light as a particle. When light energy is traveling through air, water, or a vacuum, its nature is explained in terms of waves, similar to the electromagnetic waves of radio and TV. When light interacts with a solid, it is explained as a particle and is referred to as a photon. The correct theory remains to be seen. For now, the best of both theories are used to explain the phenomenon of light and its interaction with the surrounding world we live in. Looking at figure 24-2, as you can see, light is described in terms of wavelength. Light is usually measured in nanometers and nms. Visible light has wavelengths between 390 nanometers and 770 nanometers. Below the visible lights, larger wavelengths such as UHF and VHF television waves and radar waves exist. Above the visible light rays are the much shorter wavelength X-rays, gamma rays, and cosmic rays. The actual spectrum of visible light is quite small when compared to all the other forms of electromagnetic radiation. Most fiber optic systems use infrared wavelengths between 850 and 1500 nanometers. At these wavelengths, there is less loss of signal. A typical LED has a wavelength that is between 800 and 900 nanometers, or 1250 to 1350 nanometers. Cable construction. A fiber optic cable serves as a waveguide for light. The construction of a fiber optic cable is simple. Look at figure 24-3. The fiber optic cable is composed of a glass or plastic core surrounded by a cladding. The glass or plastic core is the medium for the movement or transfer of light, of the light energy. The cladding keeps the light wave contained to the core. The cladding surrounds the entire core and causes the transmitted light to remain in the core. Without the cladding on the core, the light would be lost through the sides of the core material. The cladding and core is surrounded by a buffer area. The buffer is wrapped around the core and cladding to provide physical protection. In addition to the buffer area, waterproofing material can be inserted under the cable sheath. The cable sheath is similar to the insulated jacket on typical conductors. The outer sheath construction and materials used depend on the environment in which the fiber optic cable will be installed. Some sheaths are designed to be oil or water resistant. Other sheaths are designed to be installed in salt water or buried directly in the earth. Some cables are installed in a building plenum area. A plenum is an airspace above the drop ceiling or under a raised floor, such as those in computer rooms. See figure 21-4. Shows you the plenum area of a building structure. When fiber optic cable is installed in plenum areas, the installation usually falls under the jurisdiction of the National Electric Code. The NEC has strict regulations about the type of insulation that can be used on the outer covering of fiber optic cables installed in plenum areas. Fumes produced if this covering were to burn in a fire can be dangerous to personnel in the building.
In many buildings, the plenum area also contains the air conditioning system. This ducting would make fumes and vapors present in the plenum area harmful to personnel throughout the building.
Attenuation. Typical metallic conductors have a defined resistance value and a predictable voltage drop. They are also classified by the amount of current they can safely handle. Since fiber optic cables handles lights or light energy and not electrical energy, a new set of terms must be used to describe the transmission characteristics of the cable. The size of the fiber optic cable is expressed in micromils. The losses in transmission of signal power from one end dispersion is a distortion of the optical signal caused by light waves arriving at the termination points at different times. The light beams do not travel in perfectly straight lines, but rather reflect off the core cladding. See figure 24-6. When a signal is transmitted through a long fiber optic cable, it will suffer dispersion. Dispersion is a form of signal distortion. The signal tends to flatten out as it travels the length of the cable. As light is transmitted down the core, it is reflected from one side to side. On a short run of fiber optic cable, there is no real problem with dispersion, but on a long run, not all the light arrives at the end of the cable at the same time. The slight variation in the time the reflected light arrives can be critical at high frequency rates of transmission. A typical pulse is transmitted into one end of the fiber optic cable. Due to the reflection of the lights along the core of the cable, the light pulses at the cable termination at different times. This factor causes the original square wave to be distorted in shape. It appears flattened and elongated. A receiver equipped with a digital gates can quickly reshape the signal back to the square shape again. However, the process of regenerating an original amplitude frequency audio or video signal is not always so successful. Extrinsic loss. Extrinsic losses are caused by physical factors outside of the normal core, such as bends in the optical waveguide, splices, and connectors. Fiber optic cables have a minimum radius of bend. If this radius is exceeded, attenuation of the signal will result. Splices in fiber optic line are also special. They also need special attention. Splices, couplings, and connectors are the main reasons for transition signal losses in normal fiber optic cable runs. Splices and connectors. Small fiber optic systems can include all of the cabling necessary for the system made by the supplier prior to installation. Measurements are made and all cable splices and connectors are prepared prior to the installation. This type of installation ensures that the highest quality control standards were applied to the preparation of the cable system. However, these types of installations are not always possible. In the field, factors such as dirt, dust, and chemicals can hamper the cable splicing and termination connector installation. Splices, couplings, and connections require special equipment and techniques. The cores must be at near perfect alignment when the splices are made. Misalignments or other improper splicing will result in a loss of signal strength. See figure 24-7. A glass core fiber optic cable is cleaved, not cut, like a regular wire conductor. To cleave the fiber core, it must be scribed with a sharp cleaving tool edge made of diamond or ceramic material. Once the core has been scribed, pressure is applied to the scribed area until the core breaks. The scribe and breaking action produces a clean, clear surface at the end of the core. Traditional cutting tools used for wire cable would badly scar the ends of the core. Figure 24-8 shows a high quality fiber cleaver. Plastic core cables need not be cleaved, but an extremely sharp cutter must be used to obtain a clean, clear cut. Marks or scratches on the ends of the core material will result in a tremendous loss of light signal due to the reflection and refraction. The light will scatter in many different directions rather than transfer directly to the next cable or connector. Special equipment is utilized for making splices. The splicing equipment has an eyepiece located at the top of the tool. Since the cable diameter is very small, a microscope with at least 30 times magnification is necessary to inspect and cut the splice, or to inspect the cut and the splice. This tool is usually found in combination with tools that cut the fiber, polish the ends, and then fuse the ends together for a near flawless splice called a fusion splice. A fusion splice is the joining together of two cores using heat to fuse or melt the materials together. A fusion splicer is shown in figure 24-9. This fusion splicer performs all the functions just described and more. It is equipped with video cameras and a liquid crystal display for a close simultaneous inspection of the splice at two different angles. Where the two different materials are joined together, there will be a loss. This loss is referred to as the Fresnel reflection loss. Fresnel losses are due to differences in the refraction of each material. They commonly occur at connection points due to the differences of refraction properties of cable core material. The connector materials used for sealing the connector or air, all glass and plastic core materials, sealing materials, and air have different refraction indices or properties. This type of loss can be minimized by using a sealing material with a refraction index that closely matches the index of the glass or plastic fiber optic core material. A mismatch of sealing agent to core material can cause a glossy, exaggerated signal loss. Or a mismatch of sealing agent to core material can cause a grossly exaggerated signal loss. Care must also be taken to protect the cladding on the core when preparing cables for splicing. Damage to the cladding will result in signal loss. At times, a temporary splice may be needed. This type of splice does not need to be made to such a high degree of accuracy. In this case, a convenient method is needed for testing and laboratory purposes. One such lab splice is shown in figure 24-10 in the text. This lab splice can be used many times. It is used for conveniently make connections to metering devices in lab experiments. It is intended solely for use as a temporary splice. Fiber optic cable cores are sized in micrometers. The termination connector must be sized in accordance to the diameter of the core material. To the diameter of the core material it is terminating. Termination of cables in the field are usually made by utilizing a pigtail splicing method. A pigtail splice is a factory-made connection on one end of the short piece of a fiber optic cable. The pigtail can be easily spliced into a fiber optic cable inside a cable connection box. At times it is impossible to pull cables and their individual end connectors through conduit. The pigtail splice system is a viable solution. You can see this in figure 24-11. Fiber optic transmitters. Fiber optic transmitters are usually LEDs or laser diodes. These diodes produce the beam of light that carries the signal. Many various electronic systems are used to convert the electrical signal that drives the LED or laser diode. The light signal can be either amplitude modulated AM or pulse modulated PM. Frequency modulation, FM, does not work well with fiber optics, and it is still being refined. At present, most signals are either AM or digital. In Chapter 17, Introduction to Semiconductors and Power Supplies, you became familiar, or you should have, with LEDs. So, here we will look at the construction of a laser diode, figure 24-12. That is the left side of your screen. The construction of a semiconductor laser diode is simple. The laser diode is similar to a conventional diode. In construction, a P-type material and N-type material are sandwiched together. A forward-biased diode emits radiation at its junction or depletion region. On one end of the diode is coated with a reflective material, allowing the light to be radiated out of the other end. Laser diodes used in fiber optics have a wavelength of around 1300 nanometers. Laser diodes can transmit data at frequencies as high as 1 gigahertz or 1 billion hertz. LEDs can transmit data at rates as high as 300 megahertz, but most are less than 200 megahertz. Fiber optic receivers. Receivers use photodiodes to convert the light energy back to electrical energy. Some of these diodes are the Avalanche photodiode, the Pin Diode, or the phototransistor, and the photo Darlington, figure 24-13, top of the screen. Phototransistors and photo Darlingtons are not preferred devices for high-speed receivers. The reaction time of these devices is slow in comparison to the Avalanche and Pin Diode. The Avalanche Diode reacts to light in much the same way as its name implies. The Avalanche Diode is similar in construction to the laser diode. When the light strikes the P-type material, both a hole and an electron are caused in the depletion region. The reverse bias voltage applied to the Avalanche diode is quite high in comparison to other forms of detector diodes. As a result of the high reverse bias voltage, Only a few photons are needed to cause the diode to change rapidly to full conduction. The advantage of the Avalanche Diode is its ability to quickly go into a conductive mode. The fact that the Avalanche Diode requires a fairly high voltage for conduction is its only disadvantage. The Pin Diode, or PIN diode, derives its name from the way it is constructed. The Pin Diode, or the PIN stands for positive, intrinsic, negative. These terms describe the layers of the diode. Again, positive, intrinsic, and negative. The main difference between the photodiode and the PIN diode is that the PIN diode has a wider intrinsic layer or depletion layer than the photodiode. By widening the depletion area of the diode, the capacitance of the diode is decreased. This allows the PIN diode to react rapidly to a change in light intensity. The circuit shown in figure 24-14 on the bottom of your screen is a typical transmitter and receiver. The transmitter is a simple LED and a LED driver. The receiver consists of a PIN diode, a transimpedance amplifier, and a post amplifier. Again, the receiver consists of a PIN diode, a transimpedance amplifier, and a post amplifier. The PIN diode converts the light waves pulse, or the PIN diode again converts the light wave pulses into a varying current. The transimpedance amplifier is the pre-amplifier that converts the varying current into a corresponding varying voltage. The post amplifier is the final amplifier stage, which receives the signal from the transimpedance amplifier. Troubleshooting fiber optic systems. Troubleshooting fiber optic systems is as unique as the system itself. Two basic components are needed to troubleshoot the system: a light transmitter and a light receiver. The transmitter can be of LED or laser type, depending on the characteristics of the fiber being tested. LEDs with a wavelength of 850 to 1300 nanometers are generally used as the source. For a visual inspection, an LED at a wavelength of approximately 650 nanometers, red, is used. The transmitter and receiver are first calibrated for the type of cables being tested. The core diameter and core construction vary among manufacturers. A short sample of the cable or jumper is used as a reference. Once the receiver has been calibrated to the reference cable, testing of the system can begin. For that, look at figure 24-15. The receiver can be quite simple in design. It is used to measure the loss or attenuation in dBs or decibels. An acceptable loss for a cable is approximately 2 to 3 decibels per 1,000 feet. A rather unique piece of test equipment used in fiber optics is the optical time domain reflector, OTDR. The OTDR consists of a laser transmitter and a receiver. Light wave pulses are transmitted into the cable and reflected back to the OTDR receiver. A detailed analysis of the entire cable system can be achieved from one location. The receiver has a screen that looks much like the screen of an oscilloscope. Figure 24-16 is a sketch of a readout of a sample fiber optic system. The display of the cable system on the screen is known as a signature trace. In the illustration, an entire run of cable including splices and connectors are displayed on the screen. The sloping line is the indication of the attenuation of a section of optical fiber. The vertical spikes indicate reflective events caused by splices or connections. The vertical drops indicate the losses at the splices or connectors. The signature trace can be stored or connected to a computer to print a hard copy of test results. And looking at figure 24-16 again, it is a signature trace of a fiber optic system, which could be an example of a printout of a test for signal loss for a fiber optic cable. Moving on to the review questions for this section 24.1. First, list 5 advantages of fiber optic cable over copper cable. There are many, but some are weight, speed, durability, size, security, and we can go on, but those should be fine for now. 2, what are the 2 theories of lights? And just to name them, it's the wave theory of light and the photon theory of light. Just to shortly describe, the wave theory is basically a theory that treats light as a wave, so sort of like electricity or a sine wave of alternating current or sound, or even the waves that you see in water. The photon theory treats light as particles of either energy or actually matter that are emitted from a source, and these are particles that have, again, some type of matter. It is, however, so small that it is basically undetectable. So far, we just see the interaction that those particles have with our environments in the form of light. Question 3, define attenuation, and it is the loss of signal strength in decibels. Question 4, give 3 examples of attenuation. The 3 examples are scattering, dispersion, and extrinsic loss. Question 5, where does most of the signal loss occur in a properly installed fiber optic cable system? That is in the splices. Moving on to the next section, 24.2, lasers. You may wonder why there is a picture of an incandescent light bulb to explain the theory of lasers, but the word laser is an acronym for light amplification by stimulated emission of radiation. The laser lights is different from other forms of light because the light produced by laser is in phase. To understand what it means for light to be in phase, refer back to the chart in figure 24-2, which is supplied on your screen for convenience. You can see that each type of lights has a definite wavelength. Light consisting of all the same wavelength is called coherent light and is said to be in phase. Light consisting of many different wavelengths is called incoherent lights, light that is not in phase, and you can see an example of that on the screen as an incandescent light bulb, which consists of many different wavelengths and is incoherent light, unlike the light from a laser source. Laser construction. Look at figure 24-18 on your screen. This is a typical laser. It consists of a light source such as the strobe and a ruby. The gas in the laser can be replaced easily by pumping different gas into the resonant cavity. Different gases produce different colored beams. This is how many different colors are achieved in a laser light show. Argon lasers are commonly used in light shows because of their blue-green color spectrum. The helium neon laser is the classical thin red beam laser you've seen commonly in movies and TV. Another type of laser uses a liquid dye as its lasing medium. Many different colors of liquid dye can be pumped into the laser tube to produce different wavelengths of light. Laser applications. Lasers have many different applications. They are in industry, medicine, business, and entertainment. Construction. The laser can be used for measuring distances and alignment. Laser systems are commonly used as surveying instruments. When a laser technology is combined with a computer, the distances and angles can be recorded and stored. Calculations can be made by the computer, and a diagram or layout can be printed very easily and accurately. The laser can be used as a construction level. As a construction level, again, the laser can be used as a construction level. The beam can be rotated to eliminate a line of lights on a wall to assist the installation of a drop ceiling, or to determine the grade when removing or smoothing out land. Lasers have been used to align pipes in underground systems such as utility or storm drains. Here the light is simply positioned in one section of the pipe, and a target is set inside each pipe. As it is placed, the laser alignment system ensures the straightness and slope of the pipe. Medicine. Lasers are also used in conjunction with fiber optics to perform many types of surgery. 3 types of fiber optic systems can be inserted into a patient. At supermarket checkouts, another commonly used laser known as the ND-YAG, pronounced ND-YAG. The ND-YAG laser uses a yttrium aluminum garnet, a solid, for the laser medium. You have seen these low power lasers many times at the supermarket checkout counters, beneath a piece of glass in checkout counters, or in a handheld gun, which is a laser system used to identify product codes or on labels. The familiar black parallel lines on labels are universal product codes, or UPCs, that can be digitized and transmitted to a computer easily. For that, see figure 4-20. In this device, a laser is used to produce a narrow beam of light. The beam of light is shined on a rotating mirrored surface composed of many flat surfaces. The laser beam is reflected off of the rotating mirrored surface, causing it to flash at an accelerated rate across and through the glass top. The light strikes the bar code and is either absorbed by the black bars or reflected back down to the receiver units by the gaps between the bars. The receiver unit is a light-sensitive diode or transistor. The electrical impulse generated at the receiver is transmitted through wires to a computer where it is interpreted. The barcode data is identified or identifies the item as a number. The number identifies the item as its price. It also enters the transaction into a computer database to keep track of store inventory. CD player, another common application for a low power laser, such as a laser diode, is the compact disc player. Sometimes also DVDs and Blu-rays use these. Figure 24-21 shows this example. The beam
The beam from a laser diode is directed to the CD through an optical lens. The laser beam is reflected off of the CD to a mirror and then to a photoreceiver. The photoreceiver receives the beam and converts it to electrical impulses. The CD itself contains many tiny pits smaller than a human hair. The quantity and length of the pits varies over the disc. This information represents the recorded sound pattern. The laser light hitting the photoreceiver varies in intensity depending on whether the beam is reflecting from the pit or reflecting from the flat area of the disc. Changes in intensity moving from a pit to a flat area or vice versa represent ones. The lack of change over a period of time represents a zero. This light intensity data is converted to an electrical signal. These digital electrical impulses are converted to analog signals, amplified, and then sent to a speaker to be converted to sound. Other uses. The use of lasers is expanding every day. Experiments are constantly being produced or conducted by private industry, government, in education, and the military. We have only scratched the surface in the use of lasers. In the very near future, you will witness inventions and applications that are not even dreams right now. Laser safety. We cannot place enough emphasis on safety when using lasers. Laser light can be very deceptive or deceiving. At times, laser damage can be minimal and only cause temporary irritation. Other times, a laser may appear to be very low power and can do irreversible damage to the eye. The light from the laser does not have to be in the visible spectrum to do damage. Ultraviolet light is not detectable by the human eye, but it can severely burn the cornea. Visible light is magnified and absorbed by the retina. The amount of exposure time required for the eye damage is as fast as the blink of an eye, literally. Laser fast. In addition, the laser beam does not have to be shining directly into the eye to cause damage. A laser beam can reflect off of many different types of surfaces and result in a direct flash into the eye. Eye protection should be worn at all times when in the same room as a laser. Laser classifications. The laser classifications are the following. Lasers are classified by the maximum possible outputs during normal operation. Wattage is not the only consideration for rating power of lasers. Beam width is also a prime consideration. Laser classifications are as shown on the screen. Class 1. These beams are fairly safe to work with. These devices include the lasers in pointers, checkout counters, and disc players. Class 2. Visible laser beams only. These will cause damage if the beam strikes the eye for over a quarter of a second. Class 3. These beams will cause eye damage regardless of the length of exposure time. And finally, Class 4. Exposure to these beams will not only severely damage the eye, but skin damage can also occur. These laser beams can also cause combustible materials to ignite. Extreme caution must be used with Class 4 lasers. Eye protection must be worn when working with Class 2 or higher types of lasers. On to the questions, the summary for this chapter. But first, we'll cover the questions, which are 4 of them. Questions 24.2. Lasers can be made from solids, liquids, and gases. 2. The letters in the word laser form the acronym Lights Amplification by Stimulated Emission of Radiation. 3. How is a laser similar to an oscillator circuit? It is similar in that energy is recycled. And finally 4. Explain how a CD player utilizes the laser. And you can rewind back to that part of the section and review that. But basically, it reflects the light from the pits of the CD, and the light is reflected to a receiver which reads the light pulses. Light means high or 1. The lack of light for a period of time equals to 0 or low. Those pulses are then transmitted to a computer system which reads digital data. It is a digital to analog converter, and then out to the speaker eventually. Summary for the chapter: fiber optic cables are lightweight and corrosion resistant. Fiber optic circuits provide security. Fiber optics are not affected by magnetic fields and as are conventional conductors. Fiber optics do not pose fire hazards. Fiber optics provide a wider bandwidth than conventional conductors. The light theory of a composite of wave theory, light theory is a composite of wave theory and particle theory. 7. Light encompasses more than just the visible spectrum. There are more summary statements. Attenuation is the signal loss in the fiber optic cable. It is measured in decibels. Scattering is the loss of signal due to impurities in the core material. Dispersion is the distortion of the signal caused by the light waves arriving at the receiver at different times. The Fresnel loss is caused by differences in light refraction between different materials. LEDs and laser diodes are commonly used as fiber optic transmitters. Pin diodes, Avalanche Diodes, phototransistors, and photo-Darlingtons are commonly used in fiber optic receivers. An optical time domain reflector, or OTDR, is an instrument used to make a signature trace of a fiber optic cable signal. Laser is an acronym for light amplification by stimulated emission of radiation. Laser light is a coherent light, meaning that it's in phase. Lasers are used in industry, medicine, business, and the entertainment businesses. And finally, the eye protection must be worn when working with class 2 or higher lasers. Moving on to the testing knowledge for this chapter, chapter 24. Name 5 advantages of fiber optic cables over copper cables. We have repeated those a few times. Here is once more: the weight, the size, the security, durability, speed, and frequency capabilities. 2. Name the defects that can cause a splice in fiber optic cables to result in signal loss, and that is impurities in the actual core material of the fiber optic. Also, dissimilar materials being used, or dissimilar compounds or sealants being used, or faulty procedures of splicing, as using the wrong tool or using the wrong materials or equipment to perform the splice. And just to name a few of the defects that could cause a splice in fiber optic to result in signal loss is scattering, just to name them, dispersion, and extrinsic loss. You can find the definition for those within the material of the chapter. Do rewind to that part if need be and review. What is attenuation? That is the loss of signal strength. That was question 3. Question 4. According to the wave and particle theories, light acts as a particle when it comes in contact with a solid material, such as a phototransistor. It acts like a wave when transmitted through the air. Question 5. Name two common transmitters of light through a fiber optic cable. That would be LED and laser. Question 6. Explain how laser light differs from incandescent light. That is in phase, or it is coherent light. 7. How does the laser amplify light? That is by bouncing light waves in a medium reflected in a reflective medium. 8. List 3 applications of laser light, and one of them is cutting metal, the other one is for measurements, the other one is for performing light shows, the other one is for performing surgical procedures. 9. Name a common use of CO2 lasers, and that would be for cutting metal. 10. What precautions must be taken when working with lasers? You must protect your eyes with special equipment and eye protection, as well as your skin in some cases. And just as a sidebar, night vision devices. The military began developing night vision techniques as far back as World War II. That's news to me. The original technology required an external infrared light source, such as a flashlight or searchlight, to enhance available light. Today's night vision devices are very sensitive and do not require this type of illumination. Instead, modern devices use electronics to amplify the light from the moon, stars, and nearby lights. The viewing process involves 3 basic steps: focusing on a sensing screen, multiplying the electrons, and focusing the electrons on a phosphor screen. The photocathode starts the initial change, the photon energy to electron energy. Next, a microchannel plate, or MCP, multiplies the electrons. Then the electronic focus manipulates the beam of electrons toward an eyepiece, or charged coupled device, CCD. The electrons strike the phosphorus screen, releasing light energy. The light energy can be viewed directly through the eyepiece or on a digital display unit. All night vision devices use tube technology to pick up the image and display it, but they vary in how they amplify the electrons. In original models, the light was converted to electrons, and then the optic system focused the electrons through an anode and accelerated them so they could hit a phosphor screen, creating a visible image. Accelerating the electrons in this manner caused image distortion and decreased the tube life. First generation devices combined the 3 stages of night vision viewing into a single structure. The intensifier, tube, improved materials were used to convert light to electrons, and the units operated at lower light levels. However, these devices still had the same drawbacks of distortion and decreased tube life as the original. The second generation provided a major breakthrough with the development of the microchannel plate, MCP. The MCP is a glass disc, 18 millimeters in diameter. Fiber optics are used to create millions of microscopic holes or channels through the disc. As electrons travel through the holes, or through these holes, they strike the sides, setting thousands of additional electrons in motion through the channel. The MCP multiplies the number of electrons thousands of times, producing a clearer image without the distortion characteristics of the original technology. Third generation devices use sensitive materials such as gallium arsenide, or GaAs, as the photocathode. This allows more efficient conversion of light to electrons at lower light levels. Also, the MCP in these devices is coated with an ion barrier film to increase tube life. Third generation devices are more sensitive, smaller, and provide better resolution than their predecessors. When the night vision devices are worn as goggles, the electrons are displayed directly on a coated eyepiece. When used as a separate unit in a plane, helicopter, or tank, a CCD is used The CCD transmits digital data to be displayed on a monitor or saved to a computer. Early night vision devices did not have a bright source protection, so users could be momentarily blinded by a bright flash of light. This sort of flash could overload the tube and disable the unit. Most devices now contain a feature that reduces the voltage to the photocathode when the device is exposed to bright light sources. That is the interlude, and that is the end of this chapter. Congratulations, you have earned the high rank of Major General. That is the electronics course advanced rank of Major General. Again, congratulations, and continue your studies, as this course is almost coming to an end in the next few chapters. Thank you very much, and again, congratulations on your dedication.